document. And you can see if you're not being careful when you're building your APIs and building your applications, this can get you. It's especially interesting in the case of web service security if you're saying moving an item from a must understand to an optional place in the header processing. And this is discussed briefly in that standard. And there's a really good paper by Michael McIntosh and Paula Austell called XML Signature Element Wrapping Attacks and Countermeasures that goes into about 8 different ways to take advantage of these kind of frisky references. And again, it's not just repositioning. You can add content, you can delete content, you can add an entire another body, and it's another case of if you're not using cache reference retrieval, your application might not be seeing the same thing that your signature processor thought it validated. Transforms are the next portion here. And here we see an algorithm just canonicalizing. Extra processing instructions for arriving at a correct signature. There's base 64. We talked about XPath. What else is there? The enveloped and enveloping signatures are modeled as transforms. Not interesting. But XSLT is there. XSLT is very interesting. If you're not familiar with XSLT, it's a language for processing transforming XML. It's most commonly used to transcode XML from one format to another, from one DTD or document type to another. It's pattern matching language. You have a template, a source document, and you process them together to create a third document. When this was included in the spec, I think it was to provide an expressive means of selecting content better than XPath, and also for content like web pages that would be typically transformed by XSL before a final rendering, and you want to sign the final rendering. Sign what is meant, not what is said, the Horton principle. But they were kind of too clever for their own good in this case when they added that, because this is a really big dependency to take, and taking dependencies is a frequent source of security bugs. Your threat models don't always match up. People who built one component aren't aware that it's being used somewhere in an insecure manner elsewhere. The dependencies can evolve independently. What you thought you took a dependency on in version 1 is probably not the same attack surface that you get in version 2. So this really comes back to bite digital signatures when it comes to XSLT, because it's not just fancier XPath. It's actually a Turing-complete programming language. So it's very easy to, say, write a loop and consume infinite resources. The cryptographers designing this think in terms of pure functions, pure operations. But basically this is to determine if this signature is valid, run my code. And, I think we all can agree that that's probably not the property we want in a signature. Especially because XSLT is a constantly evolving system, and it's being used by developers to do a lot of other things besides signature validation. It was specified originally as a functional language without side effects, without I/O operations or access to the OS. So in the context of these failed assumptions, again, we're all kind of colliding here. Just another denial of service with XSLT, nothing to be concerned about. Except by design, it has network operations built in. So again, even if you change your XML resolver, you need to change it again for your XSLT processor to keep it from doing more arbitrary outbound network connections. And extensions. Turns out that XSLT typically supports extensions because people use it as a development platform, and it's a Turing-complete language. And not being able to do input-output, not being able to do all these other things is a big pain for most people. So the digital signature API developers, typically, the people developing implementations, typically would import someone else's XSLT processor, and when they imported that, they pull along all of the insecure dependencies, all of these extensions. So you get scripting, you get arbitrary file system path rights, you get SQL, you get the ability to bind XML namespaces to classes and execute arbitrary code in your platform language. So we can take a style sheet like this. This is a bit unusual syntax here, but what we're doing is we're binding in the red here the namespace RT to a Xalen extension to Java Lang runtime, and then we're going to select rt.getRuntime, and that's going to instantiate an instance of the runtime class, and then we can select the exec and Windows System 32 command.exe and run that code, all from inside of a signature. So if you want to see if the signature validates, go run command.exe. Good luck. You also can write to arbitrary files on the system. You can write to arbitrary network paths. you can embed scripting languages in JavaScript or in Bean Shell. Again, these are all valid XML that you can ship in a signature, and the processor will go and check it out, see if the signature works. Those are all examples from XAL-NJ, but just about every XSLT processor I've looked at implements a variety of dangerous extensions. You can see a list of some of them there. MSXML allows you to do scripting in any of the .NET languages. It's off by default in MSXML 6. I haven't tried the .NET framework yet to see what their defaults are. But pretty much any processor you look at is going to have things that are unsafe. And just about everybody implements XSLT. Even though it's an optional transform, the last reported interop results in 2003 showed, every major player in the field basically supporting XSLT transforms. And nobody turns off these extensions in general because most people don't know that they're there, because XSLT is too complicated a dependency. It wasn't analyzed correctly. And as a result, even if you know they're there, your APIs don't usually give you any way to turn it off. XMLSec, which is the C++ library, is the only one I've seen that has any way of doing this. Move on real quick here. Why would I execute this content if the signature is invalid? How would an attacker give this to me, assuming they don't have a key? Well, what are the steps of validation? Core validation, check your references, then see if your signature was correct. Whoops. Wrong order of operations. You assume no side effects, but we just saw there's all kinds of side effects from processing those references. And if you do that before you even see if your signature matches, an anonymous attacker can insert all those kind of commands into your signature, and you won't even know it. It's too late before you even saw that the signature is broken. Order of operations is very important here for attack surface mitigation. And I'm going to be ramping this up because I'm running close on time. So the correct order of operations here is to check and see if you have a key that you trust at all, then validate your signature value, and then process your references and see if it was okay. But people get this wrong because the specification says it the other way. That's how people built it. And so in my testing, I was able to get completely anonymous code execution in pure Java, command line execution, whatever I wanted, with a broken signature, submitted anonymously, with unrecognized key material against all of these platforms. And this advisory went out at the beginning of July. And hopefully this has been fixed, but if you're running Java, go patch your JDK. A lot of people don't do that very regularly, so now's the time. And I think this would be a great way to write a worm. You can have the same attack surface on the client and the server. You have cross-platform execution. Your old CS 101 program of writing a program that prints its own source code is solved in a single line with an XSLT feature. And you could use things like the directory interfaces of UDDI to create a propagation directory and move it around between vulnerable hosts in an organization. So would have been a good proof of concept. I didn't go there, but it's scary. Order of operations. Java exposes enough of the API to do it right if you're careful. .NET does not. And a lot of the APIs you'll see in demo code look like validate my signature and return me the key that you used. And in this case, even if the order of operations is right, it's all done and paid for before you even get a chance to see if you trusted that key or not. So that's obviously a broken API call. This is first discovered by Lawrence Bull and David Squire. I went back and did some research after I discovered this, and when I knew exactly what I was looking for, I was able to find a reference to it. But they kind of missed the boat because they were talking about it in the context of allowing completely arbitrary programs to be included as a transform and run my code completely arbitrarily. I think we can agree this is not a good idea. They said, well, you can just sign that application. Well, how do you validate the signature? Well, then you run this code and it turtles all the way down. So I don't think we want to go there. I think we should try and eliminate run my code to validate my signature from the world. What else is on the anonymous surface? Let's say we got our order of operations right. What else do we have? We have parsing canonicalization. We saw that. Key info. Haven't looked at key info yet. This is our last bit here. This is just a naked RSA key, but you can also have a key value, a key name, an X509 certificate, or you can have a retrieval method, and the retrieval method can be specified by a URI and transforms. So this isn't protected because you could sign it, but you would still need to get a key to see if it was signed correctly. And it looks a lot like a reference. including all the transforms that are supported, and this is always an anonymous attack surface. So you basically have no safe order of operations if your code is willing to resolve key info. And again, all of the APIs I've seen fail to provide you any way to turn this off. And they also punt, basically. For SSL, it makes sense to resolve to a common root of trust for the way most people use it. It doesn't necessarily make sense for XML signatures, but the APIs don't really give you a hint unless you're careful and you're reading them that this is just doing some math, and I'm not actually checking to see if I trust this key at all. And so the naive developer who uses these APIs the same way they would use SSL, assuming that they're getting some implicit trust model, isn't, and they're accomplishing nothing except proving someone can do some math. So you need to make sure if you're auditing code that the proper trust decisions have been made. And I would have liked to seen an API that kind of highlights that, maybe pass in a trust manager to the validate calls to make it clear to developers that this needs to be done. So simplicity isn't always good. This is a good case study where if you try and make your API much more simple than the actual technology that it's giving you access to, you can fail your people by not giving them access to the knobs and switches they need to make it secure. I haven't seen any APIs that give you the necessary, what I would consider the necessary interfaces to actually use this technology programmatically in a good way. You could use code access security, or you could use Java Security Manager to kind of sandbox this code, but the Java code, again, would fail recently. It wasn't set up to run in a sandbox, and most people run all their applications that do this kind of stuff in full trust anyway. XML encryption basically looks the same as XML digital signature, shares the same schema. You can, again, reference keys by references. You have transforms, you have key info. All of the same risks apply to XML encryption that just applied here. You also can do circular key references, denial of service attacks. The spec calls out you need to be able to restrict total processing time. That's hard to do in JavaScript or Java or some of these managed languages. Can we use it safely? Very quickly. Some of the applications out there specify profiles that restrict all of the knobs and whistles down to a reasonable set. The WSI basic security profile is the best of these in my opinion. If you're looking for application server products or building systems that have this switch to go to WSI BSP mode, I would do that. That's going to eliminate most of these attacks by constraining the available transforms. There's still some ambiguity there, but it's getting better. There's no simple and secure profile. This is a big problem. I would like to see this come out of the revision that W3C is doing to the standards this year. For API callers, you probably want to schema validate your signatures before you try and process them to make sure that pre-process to make up for the fact that you don't have all the switches you need in the APIs. Attack surface matters. Complexity matters. Signatures should fail fast, should be reliable, should have a deterministic profile. And you shouldn't mix class as a problem like running arbitrary code into validating basic integrity properties of a message. Relearning lessons. If you've read I said I would attribute that quote earlier properly. That was a cryptographic evaluation of IPsec by Ferguson and Schneier. You could read the whole first 2 sections of that and you would think it was written about web service security. It was actually written about IPsec 2 years before web services security came out. So we're not learning our lessons quite yet. These APIs need some time to mature. Use it where your applications demand it, but it doesn't hurt to protect things with an outer layer of SSL and be very cautious in what you accept and be demanding of your vendors and proving compliance.